Hello, everyone, and welcome to Calculus. Today, we're going to be looking at the areas between curves. So this first one is a review, just to remind you about how area and integration are connected. So if it says, determine the area between the curve and the x-axis, that's exactly what integration does. However, remember that area considered above the curve is positive, while area below the curve is negative. So if all you do is go from -4 to 4 of x squared minus x minus 6, and you don't consider the graph, this will give you the net area. And even though a problem might not specifically say determine the total area, that is always going to be implied. So I have to make the graph, and of course, it's just a parabola, so it's pretty straightforward to graph. I'm going to factor it. You could, of course, find the vertex using -b over 2a in the axis of symmetry, but honestly, all we really need are the zeros, or the x-intercepts. So -2 and 3, I know it's an upward parabola. I know it crosses way down at -6, but even that value doesn't matter because the area between the curve and the x-axis is going to be this area. Remember, it goes to 4, -4, and then this area, and then this area. So I want the total of those three areas. So I'm going to have to do the integral from -4 to -2 of f of x, I'm not going to write out the whole thing, plus the integral from -2 to 3 of f of x, plus the integral from, 3 to 4 of f of x dx. Now, of these three, which one or ones is going to be negative when you calculate the integral? This one is, because it's underneath the x-axis. So integration always finds the net area, which means this one's going to be negative. So I'm going to put a giant absolute value symbol around it so that I get the positive answer. So because this is not the primary purpose of today, I'm not going to practice for you these three definite integrals. Not only are they easy enough to do by hand, but they also could be typed into your calculator. However, in case you don't already know how to use this feature well, I am going to show you how you could do this quickly and easily on your calculator. Remember, on the AP exam, everything is about speed. So let's do. So you may remember that math 9 is what creates our integral. We're going to go from -4 to -2. Make sure you use the negative button and not the subtraction button. And then I type in my function, which is x squared minus x. Now I am using the subtraction button, minus 6. I do have to add the dx to the end, and I hit enter. So on the outside chance you don't know that that is 12 2/3, you can, of course, hit math, fraction, and it'll give it to you as a fraction, but it is the same as 12 2/3. So now I'm going to hit second enter, and I have to do it again, second enter. And by doing that, it went up 2 spots, and this saved me from having to type in the integral again. It would have been even faster if I hadn't done that little fraction step, but just in case you needed it. So I am going to go to 3, and this time I'm going to start at -2, and I hit enter. And again, if you don't know what that is as a fraction, then you can go ahead and make it into a fraction, -125 over 6. And then one last time, second enter. This is definitely faster than doing it by hand. And finally, I have to put in a 3. And why didn't that work? 3, delete, and 4. I hit enter one last time. Again, if you're not sure what that is, you can hit math, fraction, and there it is, 17/6. I want to add that to my other fraction. Now it was negative 125/6, but of course we wanted the absolute value. So plus 125 divided by 6 and plus my 38/3 for a final answer of 36.3 repeating, which again, you could change on your calculator, but it's going to give it to you as an improper fraction. So I'd like you to think of it as 36 1/3 or 36.3 repeating. Either way. So what we're going to do now is we're going to take that a step further. Instead of just finding the area between a single curve and the x-axis, we're going to find the area between two curves. So our first one is going to be the area bounded by the graphs of y is equal to x squared plus 3 and x plus 1. And then we're going to be bounded from 0 to 2. So we do want to make a quick sketch of that. You always want to make a sketch. So x plus 1 and x squared plus 3. So I'm going to do my x squared plus 3 in red. It's just a parabola. I know I'm going to want to go out to 2. So at 2, I need to get all the way up to 7. 1, 2, 3, 4, 5, 2 more. 6, 7. So at 2, I'm up here at 7. At 1, I'm at 4. So it looks like this. And then my line, which I'll make in blue, x squared plus 1. 1, 2, 2, 3, looks like that. And I'm only going from x is equal to 0 to x is equal to 2. So I could actually draw those lines, or you could just think about it as being the restriction. But the bottom line is I just want this little area right here. So how do I do that? Well, if you go back, this is going to be your theorem for it. If f of x and g of x are continuous functions, which they are, and f of x is always greater than g of x throughout the interval, then the area between the two curves is simply going to be the integral from a to b of f of x minus g of x. So it's going to be the integral from 0 to 2 of f of x, x squared plus 3, oh, my pen went a little nuts there, of f of x minus g of x. And then, of course, a dx at the end. So the question is, why does that work? Because f of x represents the height of this distance right there. F of x represents the y value, or the distance from the x-axis to that curve. And then g of x, which is really my y too, is going to represent from here to here. So since I want the purplish distance, what am I going to do? I'm going to subtract the tall one that goes all the way up to the red line, and then I subtract the blue one that goes up to the blue line, and then I'm going to be left over with the other one. Meaning, if I find this by f of x, and I find this by g of x, if I subtract them, I will find just that distance. And I want to keep finding that distance from 0 all the way until 2. So I'm going to integrate, which, remember, that is a big S. It's for sum. I'm going to add up all the subtractions, which is all these distances. So I have from 0 to 2, x squared plus 3 minus x plus 1, which is equal to the integral from 0 to 2. Don't forget to distribute your negative. Minus x, this is a minus 1, so plus 2. And for this particular one, I don't think I need to do that out by hand. You can either do it on your calculator, or because you're watching the video, you're probably not going to do it all. You're just going to write down the answer. But you can do it on your calculator. You could get some extra practice doing it by hand, but it's just a definite integral. So that's it. You learned it. There's plenty of practice problems. It goes all the way up to 17, I think. So I'm going to quick run through these slides if you'd like to write down these answers. 2 and 5, 6, 9 halves. There's the answers for 4 and 5. For number 6, 7 and 8, and 9. You might have to watch the video on. They're all together, and it's different ways of doing the same problem that you'll need to know before we do next section. Answers for 10 and 11, 12, 13 and 14, 15 and 16, and 17 and 18. So why so many examples if it's such an easy concept? Because obviously they get a lot harder, but you should try as many as you can on your own. That would be fantastic. And then only watch the video for the ones that you can't do. All right, so there is a lot of graphing in this section. You absolutely must make the graph. It is the only way to do these problems successfully. So you're going to get pretty quick at this. Let's see, x squared plus 2. But I'm only going from 0 to 1, so I'm really trying to focus on this little section right here. So x squared plus 2 is going to look like that. And y is equal to negative x is going to look like this. And I'm only going from 0 to 1. So it's going to be this region right here. So there we go. I can just do the top minus the bottom. It's always going to be the top function minus the bottom function. So x squared plus 2 minus a minus x from 0 to 1. So why does this still work even though I'm below the curve? This is very tricky for some people. They don't understand why I can still use this pattern. So again, I'm going to quick show you. If I do the black curve, then every time I do x squared plus 2, it gives me this distance every single time. And then every time I do negative x, it's going to give me the green distance every single time. But that distance is negative. But if I subtract a negative, it'll make it positive, and then this distance will actually get added to this distance. So in other words, it's kind of like self-correcting. It's just awesome. This still works, even if it's not a distance minus a distance to give you the remainder of what's left over. Even if it's a distance minus a negative distance and you want to add them together, it'll still work. So if you're going to do this on your calculator anyway, you don't actually have to simplify it. Simplifying just presents risks. And because this is not the purpose of this video, I am not going to trouble you with the actual integration. It is 2 and 5, 6. So we will practice some integrations by hand when they're more complicated, but this is not a reasonable one to spend our time doing. Determine the area of the region enclosed by the parabola y is equal to 2 minus x squared and the line y is equal to x. I don't know why that came out so tiny. It's okay. So 2 minus x squared is a negative parabola. That looks like this. And then y is equal to x. Did I make either one of those absolutely accurate? It doesn't really matter if I did, because I'm just trying to get a sense of it. So I need to know which one is on top when I go to do my integral. So this is, oh no, I was gonna color it in. So this is the area that I'm looking for. They didn't give me bounds this time, like from x is equal to 0 to x is equal to 1, because it said the area enclosed by the parabola and the line. So it's going to go from there to there. So it's going to be the top one, 2 minus x squared minus x. And I haven't been a little bit lazy about this, but there's a dx there. So the question is, what are the limits of integration? It's kind of nice when they give you a bound because then you right off know the limits. You're going to have to find them. So a little throwback to Algebra 2 here. How do we find the points of intersection? We set the two equations equal to each other. At some point, this y is going to be equal to the other y. So 2 minus x squared is equal to x. I see an x squared in my equation. What do? I set it equal to 0, and I factor. So notice I put everything on the other side. I always like to factor with my first term positive. I think that makes everything easier. X is equal to -2 and 1. Now, if you had graphed this really neatly, you would have found these 2 points. But the chances are not good that you were concentrating on finding them neatly. You were just trying to make a quick sketch to see what it looked like. So finding points of intersection is probably something you'll have to do. So I'm going to go from -2 to 1. And now that I have those 2 points, of course, you can just type that into your graphing calculator, and the answer is 9/2. Number 4, determine the area of the regions between y is equal to secant squared x and y is equal to sine of x. So some people panic. You're going to get things that you've never graphed before. We definitely have graphed secant, but not necessarily secant squared. But I want you to just think about it for a minute. First, let's get the easy one out of the way. Let's get sine. So I am going to go to pi halves just so that I can have a sense of what sine looks like. So I'm going to do sine in blue. So sine normally goes up to pi halves, and then it would keep going down. But I don't really care about that portion. I just really need to get to pi fourths. So do you remember what secant looks like? Secant is the flip of cosine. So I don't really want cosine on here, but just ever so briefly, here must be 1 because that's how high sine reached. And cosine would look something like this, right? And it would cross at 0. I didn't quite make it. And then, so secant is a flip of it. Oops, don't want it dotted. Secant is the flip of it. So what is secant squared going to do? Well, think about it this way. When it gets to pi halves, it's going to be going up to infinity. But if you square infinity, it's still going to infinity. So it still has an asymptote there. And what is the square of 1? Still 1. What is the square of 1.1? Not enough to make the general shape of it change that much. The bottom line is this is still going to be the top one, and this is still going to be the bottom one. Squaring it is still going to have these numbers get bigger. It might be a little flatter or a little steeper. It doesn't matter. It's still going to be just this general shape. So you're looking for this section right here, which is great. It's just a top minus a bottom. So from 0 to pi fourths, secant squared is on top minus sine. And hopefully now you see why they chose secant squared. They chose secant squared instead of just secant, which would have been a little easier to graph, because this is a little easier to take the integral of. So I realized that we've been typing a lot of things into our calculator. We are going to do this one by hand for 2 reasons. One, it is good practice, unlike the other ones, which were a little bit straightforward and simple. But second of all, because if you need to have a square root of 2 over 2 type answer, your calculator isn't going to give that to you. So if you need, this is called the exact value. Every time you type something into your calculator and it's an irrational number, the best you can do is write down an estimate. You could round to 5, 6, 7, 8 places, but it's still an estimate where this is the exact value. So we're going to find the exact value. The integral of secant is tangent of x, and the integral of sine is cosine. Remember, I always think to myself, okay, the derivative of cosine is negative sine. Perfect. We have a negative sine. And that's how I do it instead of memorizing them in both directions. From 0 to pi fourths. So tangent of pi fourths plus cosine of pi fourths minus tangent of 0 plus cosine of 0. I also want to make a note that sometimes when 0 is in one of these two parts, people assume that if this is 0, the answer is going to be 0. But this will give you an example of a time when that's not the case. This is 1 square root of 2 over 2 minus, this is 0, but cosine of 0 is 1. So be careful. This is 1 plus the square root of 2 over 2 minus 1, and your final answer is the square root of 2 over 2. Number 5. Determine the area of the region enclosed by the graphs of y is equal to 2 cosine of x and y is equal to x squared minus 1. So as usual, you need to start with a graph. So this is a little bit tricky to graph because normally we would make a cosine graph counting by pi fourths or pi halves, but then we also have a regular graph that we just want to put regular numbers on. So we're just going to make a rough sketch of it so you can see what it looks like. It is a parabola. I'm only going to plot that one point and then just a general shape. And then 2 cosine of x, remember, means that it's twice as tall. So instead of starting at 1, it's going to start at 2. But it's still, even though you multiply by 2, it'll still come down to pi halves in both directions. So it looks like this. And it looks like this. Now, in order to find these points of intersection, you would have to be able to solve the equation x squared minus 1 is equal to 2 cosine of x. And of course, we can't do that. So we're going to do this one on our calculator, and I'll show you how to solve it there. So I've typed in y1 is equal to x squared minus 1. y2 is equal to 2 cosine of x. I've checked to make sure that my calculator is in radian mode, and then I hit graph. And so the area that we're looking for that is bounded by these two graphs is going to be this area right here. So let's find that point of intersection. Second, calculate, intersect, which is number 5. There's only 2 graphs, so we can go quickly. Enter, enter. Now I don't know which one I'll choose if you don't move over at least a little bit on your guess, because it does intersect twice. But it found this point. X is equal to 1.265. But we need to use that exact value. AP students, this is really important that you are not allowed to round at this point. So right now your calculator thinks that that's X. Let's find the second point of intersection. I'm really hopeful that you can figure out the second point of intersection. I'm going to say -1 just to, as my guess, to get it a little closer there. Were you able to figure that out? These are both even functions. That means the value of -x is going to have the same y value as +x. So what we need to do now is we need to do our integral. So I'm going to quit out of my graph and do math 9 for integration. And remember, the last thing that your calculator figured out was x was that left bound, that left point of intersection. So I can say x. Now, I could have also stored the other one, but because they happen to be the same number, I can just say the opposite of x, and that'll make it positive again. Now, here's the important step. Which of the 2 graphs was on top? The cosine, which in my y is equal to, is my y2. So I'm going to go back here, and I'm going to select y2, and I can do that by hitting vars, right here next to the clear key, vars, y vars, function, y2. Could I have typed in 2 cosine of x? Absolutely. But you're going to have much more complicated functions than that, and you're going to want to know how to use this key. Vars, y vars, function y1. There you go. Now you don't have to worry about typing anything in wrong. And then I hit X, and just like that, I have the answer. You'll notice that I had listed 2 answers. In AP, does not matter if you truncate, which means literally to cut off after 3 places, or round. So AP will accept both 4.994 and 4.995. Personally, I prefer rounding. It seems a little bit more accurate, but by all means, if you're afraid you're going to round wrong, go ahead and truncate. Number 6, the sine and cosine curves intersect infinitely many times, bounding the regions of equal areas. Find the area of one of these regions. So as always, I'm going to start with my graph. Pi, 2 pi, negative pi, and we'll do 1 and negative 1, which is all we need to get to for sine and cosine. So let's make our sine curve. I make my 5 points of sine. Then I keep going with my pattern. So sine looks like this. Keeps going. And then cosine starts at 1. By pi halves, it's down to 0. At pi, it's negative 1. 3 pi halves, it's back up to 0. And at 2 pi, it finishes its cycle. So this is what cosine looks like. And as you can see, it is going to keep intersecting. And when it intersects, it's going to make all these regions. And these regions are all the exact same area. So you can decide for yourself which region you want to actually pick, but I would like to pick the region that's positive. So I'm going to go from here, this x value, to this x value. Do you know what that x value is? Do you know where sine and cosine are equal to each other? At what value does that happen? And the answer is at pi fourths. Sine of pi fourths is square root of 2 over 2, and cosine of pi fourths is the square root of 2 over 2. So they are both the same at pi fourths. And what's this other spot? It is 5 pi fourths, because sine of 5 pi fourths and cosine of 5 pi fourths are both negative because it's in quadrant 3. And according to my forecast, both sine and cosine are negative in quadrant 3, which makes sense. Quadrant 1 is this section, right, up to pi halves, and then up to pi is quadrant 2. And then in quadrant 3, right, from pi to 3 pi halves, look, both sine and cosine are negative there. And then quadrant 4, sine is still negative, but cosine has become positive. So if you've never really thought about it that way before, that might help you understand the forecast a little bit better. So 5 pi fourths is my other answer. So I need the top one, which is for this section right here, is going to be the blue one, which is sine. So sine of x minus the bottom one, which is the red one, which is cosine of x. That's going to be equal to the integral of sine is cosine. But since the derivative of cosine is negative sine, this is actually going to be negative. And then the next one is going to be sine. But again, since the derivative of sine is cosine, the derivative of negative sine is negative cosine, so this one's good. And I forgot my little dx here. I'm just going to add that. From pi fourths to 5 pi fourths. And we're just going to plug that in real quick. Minus cosine of 5 pi fourths minus sine of 5 pi fourths minus negative cosine of pi fourths minus sine of pi fourths. Fortunately, these are all in fourths, so the answers to all of them are going to be the square root of 2 over 2. You just have to figure out, based again on our forecast, whether or not it's positive or negative. So cosine of 5 pi fourths is in quadrant 3, so it's negative, but then with that negative, it makes it positive. Same thing here. This is also in quadrant 3. Sine in quadrant 3 is negative, but with this negative, it makes it positive. This is cosine of pi fourths, which is positive square roots of 2 over 2. But then with this negative and this negative, it becomes positive. And then same thing here. Sine of pi fourths is square root of 2 over 2, but this negative and this negative make it positive. So altogether, they have a common denominator, so I can add them up. And 1, 2, 3, 4 square roots of 2 over 2 reduces to 2 square roots of 2. That is the area of not just this region, but all, if I kept drawing it, all the identical regions have that same area. 7, 8, and 9 are all the same problem, but I'm going to show you 3 different ways to do it, and it'll teach you some different strategies for when you get stuck. So first, I'm going to make my graph. That's always the strategy. So this graph is the square root of x, and the line y is equal to x minus 2. So I'm going to put my square root in blue here, 1, 0, 0, 1, 1, 4, 2. And negative 2, negative 1, 2, 3, 4. There we go. So it says determine the area of the region in the first quadrant that is bounded above by y is equal to the square root of x and below by the x-axis and the line y is equal to x minus 2. So a lot of people read this wrong the first time. They're just so used to picking the whole area that they call it that. But if you read carefully, it says it's bounded below by the x-axis and the line, and it says it's only in the first quadrant. So it's just this space right here. So what you can do is you can make your integral. These points are 4, 2. This point is 2, 0, and 0, 0. You can do this in 2 sections. So from 0 to 2, you could just do this area. And the green line is not involved in any way. It is just the area between the x-axis and the curve, which is the way we first learned it. So just like that. Although, by the way, now I can point out that we've always been doing 2 functions. This has always been our y1, and even though we never wrote it, our other function was the line y is equal to 0. And that's why that worked, because we were stopping there. But you don't need, of course, to do that. And then you can add to it this space, which from 2 to 4 would be the curve square root of x minus the line dx. So I'm not worried about your being able to do this integration. The answer to this would be 10/3. That's choice number 1. Choice number 2 would be, so take a minute and redraw it. Choice number 2 would be to find the entire region. So go all the way from 0 until 4, and it would be the square root minus the line the entire time. And then when you were done, subtract this little triangle area right here. That would be using a little bit of geometry to simplify it. So this triangle is 1/2 base times height. Okay, so I need to make a super important point here. And that is, as you all know, I definitely sometimes forget to write my little dx's. I'm always putting them back in afterwards. For some reason, that's hard for me to remember. I will just tell you right now that if you're in my class and you occasionally forget a dx, this is not a major sticking point with me. I'm not going to take off a lot of points for it. except in one situation. So interestingly, in this situation, if you forget the dx, the answer will actually be wrong, because that dx marks the end of the integral. Without it, all of this, even with these parentheses here, all of this becomes the integral. So you have to have the dx in order to delineate that this is where the integral ends, and now you're subtracting something else. People in AP, they will not accept it without the dx in this case. If you forget the dx in this case, they would actually let that ride. So just a little note there. So that's a second way to do it. Third way to do it. Okay, this is a new skill that I need you to have for something that we're going to do with volume. Our goal eventually is to be able to find the volume of really cool shapes. So if I took this and I spun this around, don't draw this, and I spun this around the y-axis, I don't know if you can visualize what it would be, but from the outside, it would look like a cone. But if you were to stare at it from the top and look down into it, you would see this missing piece. So we need to be able to find the volume of things like that. Well, in order to find the volume, you need to know the method that I'm about to teach you. And that is, you are suddenly going to do this sideways. So when you do this sideways, these are the distances you want to add up. Totally new concept here. To add up those distances, that's the difference between the x-coordinate here and the x-coordinate here. Normally, we're measuring the y minus the y, this y value minus this y value to get this distance. So y is the square root of x. So it's the y value minus the other y value, y1 minus y2. You're subtracting the y values to get this distance right here. But now I want to subtract the x values. So if y is the square root of x, then we could say x is y squared. And in this one, if y is equal to x minus 2, then we could say x is equal to y plus 2. But now when you think about it, now you have to kind of turn your head sideways so that this is the top. That's going to look upright if you're reading it correctly. Turn your head sideways. And this is the bottom. So now which graph is on top? Now the line is on top. That's going to have the greater x value at any moment in time. This x value is bigger than this x value down here. So I'm going to integrate the line x, not x minus 2, x1 minus x2. And what is x1? X1 is y. I'm just going to erase this. I don't like that. I'm going to integrate y plus 2, because that's the one that's on top, minus y squared. In order to do this integration, what am I going to integrate with respect to? What's the variable? dy. Okay? And I have to find my limits of integration. So again, turn your head sideways so that you're reading this as the word top, upright. You want to go from the bottom to the top. So think about it, because this is where negative y is and it moves upward. We want to start here. So we're going to start at negative 2 and we're going to keep going until y is positive 2. And that'll give us that region. So now here's the funny thing. If you were to do this on your calculator using Math 9, you're actually still going to make those x's, which is a little confusing because there's no purpose in finding the y alpha key on your calculator. But we could do it by hand really quick. This is negative y cubed over 3, putting it in descending order as I go, plus y squared over 2 plus 2y. And I'm going from negative 2 to 2. So it doesn't matter that it's y's, it still integrates exactly the same way. I'll let you plug those in on your own. The answer will still come out to be 10/3. So really important example, just a little introduction of something that you will actually have to know for the future. But did you have to know it for this one? No, you could have done it either one of the other two ways that I showed you. Number 10, find the area bounded by y is equal to x minus 1 and y squared is equal to 3 minus x. So like I said, we're going to start to make these a little bit harder now that you've got the basic idea of it. So I'm going to let this one be my blue curve. So go ahead and graph these on your own. Don't just wait for me and copy it. You need to be able to graph on your own. So minus 1 looks like this. And y squared is a parabola. It'll be sideways. It'll be either this way or this way since it's not x squared. So if you're not really sure exactly where it's going to go, then just plot some basic points. When x is 3, that's going to come out to be 0. So that right there is going to be a little bit of a clue for you. 3, 0. And possibly you can look at it at the negative and say, I think it's going to go down. But if you're not sure, just make a little table and find a point that you know. When x is negative 1, 3 minus negative 1 is 4. And what would make 4 if y were plus or minus 2? So at negative 1, we have plus 2 and minus 2. So it is a downward parabola. And it looks something like this. Okay. So doesn't this look very similar to the last one that we just did? Right? So again, you are totally welcome to do it the way you know. The answer is right there. It's 9/2. You can see if you can get it. But I am going to find this area bounded by these two curves. So if you were going to break it up into two separate integrals, I do need to know, well, either way, I need to know the points of intersection. So I'm going to take a minute and solve for that. Do it over here. X is equal to y plus 1. I chose to use substitution. Y squared is equal to 3 minus y plus 1. Y squared is equal to 3 minus y minus 1. I'm going to put everything over on the same side so I can set it equal to 0. This is positive 2 on this side. When I subtract it, it's minus 2. I set it equal to 0, and I factor. And I get y is equal to negative 2 and 1. And of course, x is y plus 1. So when I add 1 to this, I get negative 1. And when I add 1 to this, I get 2. And then I take a quick look at my graph. 2, 1, that definitely looks like what that could be. So this is 2, 1. And negative 1, negative 2. Negative 1, negative 2. Ooh, bad line for me. So this blue one should have come down more like that, which is funny because when I drew it, I thought, oh, that's definitely a little off. But I wasn't that worried about it. But the question is, does the answer sound like it could be right? Yes, you're just making a quick sketch to get a sense of it. Okay, so now that I have that, I can make my two integrals. So it changes right there. So from x is equal to negative 1 until x is equal to 2, it's very straightforward. It's the line minus the curve. Okay, so this is an x. I'm going to have to switch it around. So y is equal to plus or minus the square root of 3 minus x. So this side is the y is equal to plus the square root of 3 minus x. And this side is y is equal to minus the square root of 3 minus x. And that's how you would have to do it on your calculator. Your calculator doesn't graph things that are not functions. So if you ever did want to graph this, you would have to get y all by itself on one side. And the plus or the minus is how it makes two halves. So this would be like your y1 and your y2 if you were to do it on your calculator. So this is not terrible. It's this negative square root of 3 minus x. Now, if you're allowed to use your calculator, this is not a terrible problem. But if you have to do this by hand, this is definitely not fun. And then, what's it going to be from 2 until 3? This is where it gets really ugly. You would have to do the top curve, which is the square root of 3 minus x, minus the bottom curve, which is negative square root of 3 minus x. So of course that becomes a plus, which makes sense because it's this distance plus that distance. So since it's symmetrical, it's really 2 square roots of 3 minus x, if you want to write it that way. And then, of course, my dx. This is awful, right? Awful. You do not want to do this. So now I'm going to try and sell you on this system that I taught you before. So like I said, it's optional. You don't really have to use it until we get to volume. You'll have to use it when we get to volume. But there is always a way to get around it in area, but it's not necessarily pleasant. So if you would like to finish this, I would like to see it out. So when you turn in your notes, if you don't do it the other way, I'm going to be looking for you to do this out by hand. It's awful. Okay, so let's go ahead and erase it because it's awful. And I'll show you a way easier way. All right, so turn your head sideways. You should be able to read this upright. This is the top, and this is the bottom. And then these are going to be my lines. So I'll make them in a nice yellow here. These. Oh. Everybody heard my little battery warning, of course. Every day, battery low. All right. So those are the things. So it's very simple. If you turn your head this way and make this the top and this the bottom, then it's just going to be the red minus the blue. The only thing you have to remember is to make it all in terms of y. If you turn your head sideways, you also have to turn these all into y's instead of x's. So now I have x is equal to y plus 1. And luckily, this one already was. Oh, actually, no, it wasn't. We just have to do one simple thing, though. So for the red graph, it's still the red one. But I'm going to put the x on the other side and make it 3 minus y squared. So now everything's in terms of y's. So it's going to be the red graph minus the blue graph, which is y plus 1. And what are we going from? Again, everything has to be in terms of y. I'm going to put a dy there, and I look at my graph, and I'm going to move up. When you actually make these yellow lines, they start at the bottom, and they go to the top, because we always go from negative to positive, just like we do on the x-axis. So starting at the bottom, my y value is -2. That's where I got that from. And then I'm going to go all the way up. I'm going to keep making these lines until I reach what y value? Until I reach y is equal to 1. And this is not too terrible an integral to do by hand, -2 to 1. I mean, the whole point of this, if you can do it on your calculator, the other one really wasn't so terrible. But if you're required to do this by hand, then you're gonna want to do it this way. Minus y, and this of course is minus y minus 1, so that becomes plus 2, which is -y cubed over 3 minus y squared over 2 plus 2y from -2 to 1. I plug in a 1 and I get -1/3 minus 1/2 plus 2 minus, when I plug in a -2, I get positive 8/3 because -2 cubed is -8, but then there's a negative there. -2 squared is 4, but then it's negative over 2 minus 4. And of course, this becomes a -2. So I have my -1/3 minus my 8/3, which is -9/3, which is just -3. And then I have my plus 2 and my minus 2. What does this come out to be? plus 2, and these two are negative 6, so plus 6 is plus 8, but then minus a half. So 5 minus a half is 4.5, which is 9/2. So if you had to do it by hand, there you go. Okay. If you are in AP, here's the really exciting news. If you're in my class, you better be writing all the way down to 4.5 if I ask you to do this by hand. But if you're in AP, you are never required to simplify your answer. You still have to finish the problem and make it entirely numeric, but all of this stuff can go. So you could box this answer. I'm not kidding. Okay, if you're in AP and you go any further than this step, you're just risking your answer. Because if you go from here and accidentally write 5.5 instead of 4.5, you're going to lose a point. So you definitely don't want to do more than you have to. They will accept any numerical answer, even if it is not simplified. Okay, number 11. Find the area of the region enclosed by the graphs of y is equal to x cubed and x is equal to y squared minus 2. Looking ahead to the answer, I can see that we didn't do it by hand, we did it on the calculator, which probably means that these don't intersect somewhere that I can tell. But we can graph them really quick. So doing it by hand, x cubed is something that we're pretty familiar with. Looks like this. And then x is equal to y squared minus 2, or y squared is equal to x plus 2 is some kind of a sideways parabola, right? You should be able to figure out now that it's going up because x is positive and that it's been shifted 2. So if you're not exactly sure where it lands, then just make a little table of values. When x is equal to 2, that would make this side 4, which means y would be plus or minus 2. So at 2, it's going to be plus or minus 2. At negative 1, this side would be 1, which would be plus or minus 1. So when x is negative 1, y is plus or minus 1. Oh, I see a point of intersection. And when x is negative 2, it's going to be 0. So these aren't too hard to graph. But you might have trouble finding that point of intersection. This one was easy, negative 1, negative 1. But you still got to find that point of intersection right there. So this would be really hard because you'd have to get either y or x all by itself on one side. And you could do that if you made this y to the 1/3 is equal to x. Then you would have, substituting in this right there, you would have y to the 1/3 is equal to y squared minus 2. Not that this can't be solved, just not something that you do on a regular basis. So of course you think, oh, I'm just going to do this one on the graphing calculator. Yes, you definitely want to do this one on the graphing calculator. However, you still have to be able to switch this to something that you can type into your calculator. It will not accept non-functions. So you're going to have to take this y squared is equal to x plus 2, and you're going to have to change that to y is equal to plus or minus the square root of x plus 2. And then you can make your y1 the positive root, which is this side, square root of x plus 2. And you can make your y2 negative square root of x minus 2, which of course is the bottom one, negative square root of x minus 2. But now you still have another decision to make. Way 1 in doing this problem would be to go from negative 2 to negative 1 and do the top one, y1 minus y2, and then add to that from negative 1 to a. We're just going to call that a for now because we don't know what that is. We'll call this the point AB. From negative 1 to a, now this one's on top, y1 minus, and you can mix it up here. You can say, I guess I need to put parentheses, x cubed, or you can say y3 is equal to x cubed. It's up to you. As long as you've marked what y1, y2, and y3 are, AP will completely accept this as an answer. Even though you're seeing y's, these are x's because those are the names of the functions. We're not actually doing things in terms of x. So we'll find point A on your calculator in a minute. Way number 2 to do this problem is to look at it sideways. If you look at it sideways, and this is your top, now you're going to be going from -1 all the way up to B, and the entire time the cubic function is on top, and the entire function, the entire time, this bottom one is on bottom, which we actually can't do in terms of y. So you would have to switch this around. X is equal to cube root of y. So this would be cube root of y is the one on top, and then the one on bottom would be your parabola, which is y squared minus 2. So you can decide which one you want, but either way, we need to find A and B. So let's go ahead and do that now. So I've typed in the 3 equations, x cubed plus the square root of x plus 2, you don't actually need a plus in front, and then minus the square root of x plus 2. You'll notice that I do have to have a little negative key. Make sure you use the negative and not the subtract. So I hit graph, and of course it shows the exact graph that we've already come up with. So again, if you're trying to figure out the points of intersection, you're just going to use your second calc feature, which I think most of you are really good at by now. But this is going to be, I think, the first time ever since you were back in Algebra 2 that you're actually going to have to really think about this first curve. This is the first curve, and that is the second curve. But if you had done this backwards and it couldn't do that, this is the button you want to use. This little arrow will flip between what you want the second curve to be. So make sure that when there's more than one curve that's having a point of intersection, you let it know. That's the only point of intersection. You can just hit enter, and it found it. If we hadn't graphed accurately and we hadn't been able to find the other one, then you would do the same thing. Second, calculate, 5. First curve, it's written up there, x cubed, enter. Second curve, not this one anymore. Now I want the black one. If yours isn't color-coded, it says it up there at the top, which one they're talking about. And you can hit enter. You don't need to guess. And it found it, -1, -1. Now, I personally do want for it to save this other value. So I'm going to go back and intersect with the first curve and the second curve again, because I want my calculator to think that that value is x. That way, when I quit this and I go to do my math 9, and I go from -1 to x, it already knows what x is. So as long as you've just used the intersect feature, it's fully aware. So again, just looking at my graph, I need the red one minus the black one. If you can't remember what those are, you're going to have to write it down somewhere, but I can just go back and look. So it's definitely y2 minus y3. So I can go back to this. And one last time, vars, y2 minus the actual negative key, like the actual minus key, y3, vars, y3 dx. And then plus the integral from that same x to, no, actually only from, oh, I did the other one wrong. From the other one should be from -2 to 1, and then from -1 to x. So I actually need the first one now. So this time, well, I guess I'm right here. Just to put it in order, I'll change it here. So this one went from -2 up to -1. It doesn't actually have to be in order. Just trying to keep it consistent. And then this one's going to go from -1 over to x. And now, which two functions am I doing? Now on this little interval, it's the red minus the blue, which for me is the y2 minus the y1. I forget that every time I leave this screen, I have to scroll over. So y2, how do I get that? Vars, y vars, function y2 minus vars, y vars, function y1. And then don't forget your x. 4.214, or if you round, 4.215. Okay, this is the last one we're going to do in this video. So obviously the first step is to make a sketch. It is a little bit different. 2, 3, 4. So we're going to draw the line x is equal to 4, which looks like that. And I'm going to draw the parabola x is equal to y squared. Again, you should know by now that y squares are sideways parabolas. It's positive, so it should be the one that's going up, and up for y, that is. And we can plot a few points. So 0, 0 is going to be on there. When x is equal to 4, y is going to be equal to plus or minus 2. So there's 4 plus or minus 2. And another easy one would be 1 plus or minus 1, just to give it a nice shape. You probably recognize those numbers. 0, 0, 1, 1, 2, 4 is how we always did it on the other direction. So couple different choices on how to do this one. We want this entire region here. So I know after the last couple examples, you're probably thinking, oh, she wants us to turn our head sideways and not have a top part of the parabola and a bottom part of the parabola. And that would be excellent if you could figure that out. So this is the point for -2. This is the point for +2. This is the point 0, 0. So if you did look at it sideways, then the line x is equal to 4. So remember, it's always what x is equal to. So since x is equal to 4 is always on top, and the parabola is always on the bottom, and you're going from -2 to 2, this would be very, very easy to do, okay? But just to show you that you have options, you could actually do the area under the curve from 0 to 4, but you wouldn't have to do the top curve minus the bottom curve. You could just do from 0 to 4 and ignore that completely, just a single curve of y is equal to the square root of x. And then you could double it. So think outside the box a little bit. If you would rather do that one, you can. It's up to you. But I do want this one done by hand. So now you have to ask yourself, ooh, which one can I do by hand easier? So I don't know. I guess I'm not actually going to time it, but if you did this one, it would be 4y minus y cubed over 3 from, actually, I can double this one also, right? These two sections are the same no matter which way I do it. Why is that a benefit? Because then I could plug in a 0, which is always nice. So I'm going to multiply by 2, and I'm just going to go from 0 to 2. So now I have 2 times 8 minus 8 thirds, which is 16 minus 16 thirds, which is 48 thirds minus 16 thirds, which is 32 thirds. Or x to the 3 halves divided by 3 halves. And now we decide to stick that 2 out there. So 2 times 2/3 x to the 3/2 from 0 to 4 would be 4/3, and then x to the 3/2 is square root of 4, which is 2, cubed is 8, which also gives me 32/3. All right, lots of examples in this one, but I hope they all helped you really master this concept. Have a great day.